Performance and operation. Accuracy and repeatability. SKMs are significantly more repeatable than they are accurate. They have positioning accuracies for industrial manipulators ranging from around 10 mm for uncalibrated manipulators to 0.1 mm for calibrated manipulators, and positioning repeatability from around 0.2 mm for large spot welding robots down to 5 micrometer for precise micropositioning manipulators. Generally speaking, the repeatability is about one order of magnitude higher than the uncalibrated accuracy of an industrial manipulator that you can purchase. This leads to the fact that industrial manipulators are usually programmed in a combination of online and offline programming.
We want to discuss the possibilities to program these robots in this factory. Let's have a look how this robot is programmed by the playback method, also called vt2021, which is typically associated with continuous path control. The programmer leads the robot manually within the desired path regarding the orientation of the robot unit. At the same time, the controller stores the current position and visually adjusts the point periodically. That means after certain microseconds. The advantage here is even complex paths can easily be programmed with full-scale programming.
This is a type of online programming that is repeatability dependent, which means that the robot will presumably be significantly closer to the position where you would like it to be as if you were offline programming it. But the disadvantages are also obvious, and that is that you are not able to transfer a task program, that is the program that the robot executes, from one robot to another robot, as well as that you are then scheduling a lot of downtime for your robots because, as you see, someone is actually manually operating the robot.
Such as spray painting and contour welding. Here, the robot is positioned to the desired points by means of the control panel, also called T-square. When the operator has the desired position and vehicle of the robot, the operator can see these coordinates by positioning the spot of the safety screen. Due to security reasons, the robot is always never the same position. Because the operator was within the working area, that control panel must be built with a nice high independent switch. Typical applications, therefore, are spot welding and pick and place. Here, you get an overview of the advantages and disadvantages of online programming.
So, just going quickly through the ones of online programming in terms of advantages. Yes, the programming is illustrative. You will be very unlikely to create collisions, and it is able to detect inaccuracies. Well, I would rather say it is repeatability dependent. So you will already lead it to the position where it needs to be, and thus your task will be more likely to be successfully executed. That you are able to do it without further programming experience, that is an arguable point, I think. Disadvantages. The robot workspace is occupied during programming, and it may not only be the robot workspace, but whatever other facilities are cooperating with this. Not only integrating additional information such as sensor data is difficult, but you can also not communicate information such as acceptable variations. Also, creating complex programs is difficult as you do not have the opportunity to choreograph loops or conditions into this programming method.
Here, you can sit in your office. The movements of the robot are simulated within
And if you're using offline programming, you have the difficulty that you're actually dependent on the accuracy of the industrial manipulator, which means that while you're not occupying the robot and you would be able to transfer the program that you've written from one robot to another robot, the problem is that your task may actually not be successfully executed because your end effector or your tooltip is not where it is supposed to be. That is, your simulation does not accurately resemble the real world. That is what may happen. Or on the other hand, you may not have a calibrated robot, meaning that your robot will not be able to get sufficiently close to the position that you specify. So, and why does that happen? Well, that happens because the robot calculates the position that it goes to based on forward and inverse kinematics. Let's just quickly walk through this. So we said before that a robot, or a serial articulated robot, usually with 6 degrees of freedom, has 6 rotary degrees of freedom, which you see here, named θ1 to θ6. We are interested in seeing where the mechanical interface goes, and thus we are writing a function which depends on the parameters of the robot, such as L2 that you see here, that combines the movement of the 6 joints to the positions and orientation in space. Calculating the position in space based on the known angles θ1 to θ6 is called forward kinematics, and if we have a position that we would like to achieve and are thus identifying the angles that we need for that, we call that inverse kinematics. This transformation between the joint space and the Cartesian space. The Cartesian space is the space that we humans tend to think in, that is moving along 3 mutually orthogonal axes, x, y, and z, leads also to the effect that industrial manipulators commonly encounter kinematic singularities. A kinematic singularity is a moment in which the industrial manipulator instantaneously loses the ability to move in one or several directions. We will discuss kinematic singularities in greater detail in laboratory number 1, but one aspect that you may want to consider is that once you find your industrial manipulator to be in a kinematic singularity, you cannot use the Cartesian jogging mode in order to move away from there. That is, at those positions you cannot move in x, y, and z. However, you can still move in joint space, that is, actuating the angles θ1 to θ6 individually or jointly. Back in the days, the proximity to a kinematic singularity used to be more difficult than the actual kinematic singularity, because at a kinematic singularity, the industrial manipulator uses the ability to move, while in the proximity to a kinematic singularity, the industrial manipulator would tend to speed up its movement, and also the movement would become unpredictable. So, for this, we need a robot model. And the robot model might feature errors. Those can be kinematic errors and they can be non-kinematic errors. Kinematic errors, for example, are, we have seen before that the position is dependent on the parameter L2, and let's say the designer has designed L2 to be 500 millimeter, but is produced to be 500 millimeter and 50 micrometer, then there is a difference in the delta, and you can think that if you have 7 links and you do not only have the differences in the length, but also you have some angular errors, those quite quickly build up to a couple of millimeters, dependent on the reach of the robot that you're actually having. Thus, people tend to calibrate industrial manipulators. This is an research industrial manipulator where they would like to achieve the highest accuracy possible. So they are using a lot of measurement instruments in order to identify not only these kinematic parameters, but also other parameters that have been outlined in the error sources before, as for example, the joint stiffness of the manipulator or its thermoelasticity, meaning that how much do the links expand due to the power consumption of the motors, or by employing, as we said before, additional sensors, such as a double encoding on the joints. Here you can see the calibration of the robot and the end effector by using a laser tracker. And then finally, this robot is used in order to drill holes into the part of the airplane fuselage. Once you accurately know those errors, you can feature them in your manipulator models, meaning that your model will be much closer to the actual robot that you're using, meaning that you can use offline programming more accurately because the accuracy of the robot gets closer to its repeatability. This process is referred to as robot calibration or manipulator calibration, which is the process of defining an applicable mathematical model and then identifying the different model parameters such that the model describes the actual robot as good as possible. Generally speaking, it consists of 4 steps: the modeling, which is general, the measurement, which needs to be done on each individual manipulator. Then you have the identification, where you use the measurement data of each individual robot together with the model in order to identify the model parameters such as joint stiffness or the length of the parameter L2, and then to implement them in the robot controller to improve the accuracy. We're going to have a look into this in the first laboratory in greater detail. Here you can see some examples of research being conducted on the improvement on the positioning accuracy before and after calibration. And you can generally see that the mean positioning accuracy before calibration ranges somewhere to close to around 1 millimeter or close to 2 for the maximum error, and is then decreased significantly by a factor of 6 for the mean, or by a factor of 3 for the max positioning accuracy after calibration. Most commonly, the manufacturers of industrial manipulators offer also calibration services, and they then provide you an accuracy that is better than 1 millimeter. That is, that the maximum error that you may expect is 1 millimeter. Usually the mean is much closer to than around 300 micrometer, such as in those examples of research works. If you're interested in this, please feel free to consult some of this additional information